Thank you, Stefan, for the flattering introduction. So just a bit of context, I didn't manage really to time my medication very good, so you might see some strange movements from me, so don't worry. I mean, that's just my condition. Hopefully at the end of the presentation I'll be able to walk, but not now. Anyway, get into it. So today I'm going to talk about software and swindle games. What is this all about? So a bit of context about me. So first, I think I owe you to give a little bit of the context of my project. I'm the tech lead for the Swarm project for the Ethereum Foundation, and set the context for what we're going to talk about, which is actually a sub-project of the Swarm team and our Swarm project. So first let's go to the status, and then and after that I'm going to talk about, jump into the software and swindle games, actually. So first of all, what is Swarm? The Ethereum Foundation and the founders kind of early on that the public blockchain, Ethereum blockchain, is basically the final missing piece in the puzzle for decentralized the decentralized internet as a whole, because it can provide the what was really missing in decades of peer-to-peer technology research. Basically, the incentivization layer. So it provides the word computers, processing the Ethereum blockchain to be able to program incentive systems, which can make the peer-to-peer systems kind of self-sustaining with providing economic incentives. And that's why kind of they envisage this kind of funnily called holy trinity of the Ethereum ecosystem, which is the public blockchain on one hand, and the Swarm for document storage and content distribution on the other, and third, Whisper for communication. So this is how the narrative started with Swarm originally. That now you consider the Ethereum blockchain as the word computer's central processing unit, the word computer CPU. Then what else is missing from that word computer? Well, hard disks. Swarm will be the word hard disk. However, this narrative, I'm leaning towards changing this narrative a little bit, because the Swarm project on the way realized that a lot of the technology that we use of good design, and a lot of interesting solutions fell out of it, and now the scope of the Swarm project is slightly more ambitious, and we're trying to provide all kinds of base layer services for Web3, for the decentralized web. What is it that I'm talking about? So first of all, as Swarm, as a decentralized, really decentralized and distributed document storage and content distribution system, shares a lot of good properties with all the other efforts in the field, like including BitTorrent itself. So it brings what you expect of it, like the promise of a zero downtime fault-tolerant system, which has censorship resistance due to the fact that content is redundantly stored, distributed in the network. So the authorities have no way to knock on anyone's door to bring down any site or anything that's not of their liking, and that's an important property to protect freedom of information. And more interestingly, also there's auto-scaling, which just, without any further explanation, just means that popular content will replicate more and will be more spread out in the network, and as a corollary to that fact, you have lower latency of retrieval when you want to retrieve those assets. And most importantly, it promises self-sustainability, which means that we're going to design some incentive, well, actually we design some incentive systems which can provide economic incentives for the participants to share their resources, notably share their bandwidth, to facilitate fast and responsive retrieval and relaying of messages. And secondly, provide insurance for preservation of files. So for example, the old problem of like how you make sure that if you want to store in Swarm, like files that you don't access very often, so to say, rarely accessed files like your birth certificate or your grandmother's family album, how you make sure that these are preserved in the face of the opportunity presenting to storer nodes to store more popular content like all the lolcats in the world. And this kind of insurance system is one of the pillars of this self-sustaining property. So this is a bit of context, and let's see now what I'm talking about when I say that the scope of Swarm is slightly wider than originally conceived of in the context of being the world hard disk. Well, of course, apart from document storage, content distribution, virtual hosting, which are the primary elements that I mentioned, now we extended our scope to 3 more areas. Basically, internode messaging, which is the PSS protocol, PSS. I'm not sure I'm going to talk about this too much. There's also in the pipeline quite comprehensive support for decentralized database services, notably indexing and provable creation of certain views of data and processing, aggregating various data sources. And thirdly, support for all kinds of digital service supply chain economies in general. This is actually the topic of today's talk. What I'm talking about here is basically support that if in the network you want to have a network of service providers that provide some sort of digital service, there are some basic functions which you might want to be able to use. For example, payments and some sort of service guarantees. Service guarantees with the whole shebang of enforcing those service guarantees, issuing the service guarantees, verifying, etc. And of course, the payments should be, I mean, these days, we have the public blockchain for secure payments. So I wouldn't even dare to mention payments if it was not in the spirit of making a scalable system of off-chain payments, which means that this is the usual spiel now that I have to mention that there are problems with the blockchain. Everybody knows that even blockchains with the promise of sharding and proof of stake consensus, it's kind of doubtful that as such they can cope with Visa volume transaction volumes similar to what Visa or MasterCard processes. This is the usual caveat that people mention. And of course, the remedy to that is there has been proposals in the blockchain space, usually based on side chains or state channel networks. Our solution, the swap and swindle games framework, is our flavor of a kind of state channel flavored approach. I will talk you through this. So basically, in summary, the support that we want to give to digital services is a scalable and robust payment system off-chain, and also a system of service guarantees that are enforceable. So I'm going to skip this because this slide just goes through the properties of Swarm and kind of boast about how efficient it will be. Of course, it's a little bit void without having a working proof of concept. At the moment, the status of the project is we're basically in alpha. So the currently working Swarm has a test cluster, which is kind of working. The next big release is POC, proof of concept 3 release, which I kind of planned it to come out to be released before DEF CON. It's not going to happen, so hopefully it's going to be released this year. And the proof of concept 4 is, according to my plan, the pre-release for the recommended production version of Swarm. So it's kind of let's call it beta. And what you see on the diagram is just the various APIs that how you can currently use Swarm. In the middle, that's the most important one. You have a HTTP proxy interface that you can interact with Swarm from decentralized applications and all kinds of scripts. So these slides just detail the features that's going to be included in the proof of concept releases, and this is the theme. Now I move on to the second part of the talk, which is exactly about this swapware and swindle games framework. So what is this all about? This playful wording for swapware and swindle is just feeds into my obsession with acronyms. I like to entertain myself with acronyms, which the acronyms that I use have to be themselves words which are meaningful and also functionally and semantically related to the concept that they stand for. So it's a very restricted game. And in this case, the swapware and swindle kind of map to three aspects of this framework and this system. Hopefully it's kind of mnemonically relevant. So swap is the part where peers in a network kind of swap certain instruments, like they issue checks and service requests, and they swap, transact, like issuing this and receive from the other. So this kind of a local interaction of various instruments. So that's one part of it, is the transactional communication component. The swear component is the ability to actually promise, to commit to a service contract, some sort of agreement that you keep yourself to, and to collateralize that promise, you put up a deposit to a contract on the blockchain, and you stake. You stand to lose it in case of foul play, in case you found cheating, or you make a mistake, or your equipment dies. Then you can be held accountable for not complying with your service promise. This component that manages that is called swear. And the swindle component is the actual judge part that takes care of enforcing the service contract. It basically implements a kind of courtroom type system. Maybe we're going to go into that a little bit more detail. It's kind of a courtroom system inspired by the paradigm of blockchain as a judge, which means that in most normal operation, we assume that things are going fine. Only in the case of some trouble, you report, you basically sue the person. It's like in the real world, a trial. You basically start a litigation where you challenge the service provider that they didn't comply with their own with the rules that they sworn on, and there's this component kind of orchestrates the trial, asks witnesses for testimonies whether it's true that they didn't comply with their promises, and finally they come up with a guilty or non-guilty verdict, which is passed back to the registry component, which can execute a sentence assigned to that particular verdict. In this sentence is in the most usual case, it's just forfeiture of your deposit, and usually the exclusion from the game. It's like you lose some reputation points, definitely. So this is the overall context. So this whole thing can be characterized as, this framework characterized quite ambitiously, maybe a bit glorified way, but it's a kind of scalable base layer infrastructure of decentralized service economies. And these are the three components I talked about. So what is swap? Let's first go into the first component, the swap. So swap is, first of all, offers an accounting protocol, which is a tit-for-tat accounting between peers. It's a peer-to-peer accounting system, which first of all allows you to exchange service for service. So it's in the case of bidirectional service provision. What are good examples for that? The best examples are the bandwidth, like relaying data in Swarm itself, so basically sharing bandwidth. When I request, I watch a movie and I request, chunks of a film, like certain data blobs that are part of a film from my peer, then I pay for it, which means that I just account like, yeah, I gave you, I took one chunk from you, and when that person also, watches their favorite show, then they will request certain chunks, and some of them will be relayed through me, and therefore, like I get my credit for serving them that chunk. So for service provision, it's a very simple tit-for-tat accounting. If the service consumption and provision are roughly equal over time, and there's no variance, then basically this system can get away with not touching the blockchain, but not doing any kind of payment. Obviously, this is very lacking in business, because most of the time the traffic will be tilted, and one party will eventually substantially consume more than the other, at least throughout a certain period of time. So this is when we introduce a kind of delayed payment instrument that we combine with this swap accounting protocol. A delayed payments instrument is a simple checkbook. That's what we start with, and we're gonna build up this whole system from like very small and very simple ingredients, like as if we built up a castle from like little Lego pieces. And so the checkbook is exactly the same as a real checkbook. So you can issue it, you can sign a check to a beneficiary with a particular amount, and if you operate a checkbook contract, and in the same way that you go to the bank and cash your check, you send the check, this signed note to the checkbook contract, which verifies it, and if the balance checks out, it transfers you the beneficiary the amount. However, of course, the interesting thing is that with giving the checkbook, I also give you the opportunity to not necessarily cash it right away, but give you the opportunity to hold out and therefore save on transaction costs. Now, the interesting properties of this checkbook, very simple checkbook contract, it's actually really beautiful that such a checkbook contract is basically 5 lines of active code in the Ethereum, in the Solidity language, and I think it's kind of a really, really beautiful demonstration of how powerful this can get. So once again, anyone can send in like the check, and the problem with that is that, of course, the checkbook is not containing any kind of payment guarantees, right? Just like in the real world. If you zero your account, then of course the check that you gave me earlier will bounce. So it has limited guarantees, limited liability, but of course it's better than nothing, because it's explicitly at least acknowledging that I owe you something. So by not having money on your checkbook account and your check bouncing, you basically admit to basically cheating, because you didn't have any resources. And this is exactly what happens. So when a check is cashed and the balance is not sufficient, there is no sufficient funds on the checkbook contract, then the checkbook contract defaults, and your reputation or your identity attached to that checkbook is basically void. So let me turn to this diagram, because this explains to you the interaction between the swap accounting and the checkbook. So basically, take the two peers that interact and exchange service for service. They have a certain tolerance threshold, which say that, okay, I allow you to get like 100 chunks from me, but if you get more than 100 chunks, so if our relative balance is more than 100 chunks, then please pay to me back, because that's indicate that you consume more. So in this case, the orange range is the free range where things can move without anyone paying anything. But when you get to the end of the orange range, so in this case, the vertical fat line indicates where we are in the relative balance. So in this case, peer A is actually consuming more. And in this case, if you reach the payment threshold, that's one of the dashed lines, then you're obliged to send a check to the other person. And when they have the check, they set the swap balance back to 0. Yeah. What do they do with the check? I mean, first of all, of course, they can be very cautious and just cash it on the blockchain. But it's not a very clever thing to do, because the whole point of checks is that you can hold out with the payment. And the other property of this checkbook contract is that if you accumulate several checks, then you can cash them in bulk, because basically they record the overall total cumulative balance owed to the counterparty, to the beneficiary, and that's why it's always enough. It's always sufficient to send just the last issued check and get all that you are owed. You don't have to actually carry all the checks that you accumulated with you to the bank. Okay, so what do you do, of course, if the other person doesn't issue the check? Well, you have a certain leeway. You have a disconnect threshold, which is basically some sort of either time or consumption limit. So when they reach the 100 limit, for example, and then you expect a payment. If they reach 120 and you still didn't get anything, then you disconnect from them and you never deal with them or do whatever you want with, like, some recording, some reputation points with them. Okay, so so far so good. Is it more or less clear so far? Yeah. So this is actually the timeline sequence and timeline diagram. What's happening? So there are like 4 entities in the 4 vertical columns. So just for you to understand clearly, the ones on the side that are called A client and B client, they are the off-chain representation. So these are the entities that are off-chain, that are in the peer-to-peer network. They're basically exchanging these checks. And the middle 2 columns are actually the swap contracts or checkbook contracts that are on-chain. So the green stuff is happening on-chain, and the red stuff happening off-chain. So here what happens is the first line says that you issue a check, this time passes, and the client B decides to redeem the check. They send the check in a transaction to the blockchain to A's, to the issuer's swap or checkbook contract. And what that does is simply does an Ether transfer if the balance allows it, and that generates kind of log events which the clients listen to, so they get notified of the withdrawal and the transfer. So this just illustrates a very simple sequence diagram of what's happening. Now, what's another interesting feature is that you can use this system to actually not only hold out payments with the checks, but actually pay with the accumulated checks from the other person. So let's assume that we consumed so much that I ended up with 3 checks from you, and I piled it up. I actually kind of trusted or watched your balance, and I held out not cashing them, so it's a pile of uncashed checks. Now I started consuming, and the balance tilts, the swap balance tilts towards me being in debt. And what do I do with that situation? Well, it would be nice to have some instrument where I can waive the checks and say that basically I don't want to pay you with the check, but actually let's destroy your check that you gave me. I promise that I will never cash it. This construction is called a waiver. So basically what happens is that as the consumption goes back and forth, you exchange checks and waivers, and this is how you settle the balance. Of course, these all have like secure versions of how you can actually settle. So when someone sends in a check, in a checkbook contract that allows waivers, you can send in a check, and that puts the withdrawed funds in a kind of escrow state, and expects the other person to send in waivers just in case. So just in case your counterparty wants to run away with the check amount, but they actually already waived it because they assumed some service from you. Is this understandable? Yeah. So in this case, you collect waivers and checks, and they pay off. They pay it off against each other. So of course, you can enrich this construction with an actual on-chain balance, which you dedicate to a particular peer. What does this mean? So far we talked about a checkbook contract. A checkbook contract has an overall balance, but you have several creditors. I can issue a check to Julian. I can issue a check to Fabian, and the balance, the overall global balance of the checkbook, is a collateral that's pooled over all my creditors. So in case they have no way of knowing about each other how much I promised in checks to each other, so they basically have no way of telling whether the checkbook is solvent if they run the bank to cash the checks. So what's a possible solution for that? Well, they might want to ask me as the issuer to dedicate a particular deposited amount just to them, so that they know that I can issue like a checks up to 1,000 Ether, and they can still be sure that locked up amount will cover and collateralize that debt. So they can hold out not cashing the checks, but they'll still be 100% sure that they will have the money. Is this okay? So basically they dedicate a so-called hard channel deposit to a particular peer. Now, if you have two checkbook contracts that refer to each other, like I have a checkbook contract and I have an entry with a hard channel deposit towards Fabian, and Fabian has one for me, for my checkbook contract, then basically these form two halves of a full payment channel, and this construction basically implements a proper payment channel. I don't know if you guys heard this notion of payment channel. The payment channel is exactly this construction. Usually it's implemented with one particular contract that's taking care of the traffic between two individuals. In this case, we kind of simulate a payment channel functionality with entries in two checkbooks. Now, the interesting thing starts here. Actually, can we have like 5-minute break, because is that okay? Just a little bit, because my hands are really shaking. I think I need to take some meds. Just give me 5 minutes. Okay. Thank you guys for bearing with me. There's a bit of intermezzo needed. So I skip the details of these deposits because we might return to that. Let's move on to this one. So what is this about? We talked about checks so far and waivers, but in fact an extension of this whole checkbook contract can handle various kind of instruments that basically I subsume under the name of promissory notes. So promissory notes implement various instruments. For example, basically loan requests, which I call bonds. They implement authorizations, which are basically authorizations for recurring payments. They implement what's going to be more interesting here is like conditional bonds and bounties. So conditional bond is basically a bond, like a promise for future payment that is assigned to an escrow witness contract. What does that mean? It means that the future delivery of that service that you request is going to be judged or countersigned by this escrow witness contract. This contract is a simple solidity contract which conforms to the generic witness ABI, which means that if a contract implements the witness abstract contract, if it has a testimony function, The testimony function, I mean, it doesn't matter what kind of arguments it's called. Basically, the witness is testifying whether you delivered the particular promised service or not. Yeah, and based on the testimony of this witness, you are entitled to a positive reward attached to that service request. Yeah. So what are we talking about here? Like, what are the examples of such decentralized services? Well, for example, imagine a decentralized database service supply chain where you have like indexers, and you have a travel agency which issues kind of travel offers, and you want a flight aggregation service which simply aggregates your offers in an index. So you put up a conditional bond, which is basically a service request that refers to a particular escrow that can prove that you did the work properly, and when the service is delivered, the person can come for their money if the service was actually provided. So a conditional bond corresponds to a service task or service request. And there's a variant of this, like what I call the bounty. A bounty is exactly like a conditional bond. The only difference is that it has no particular specified beneficiary. It's just kind of shout out in the air, like whoever solves this problem will get this bounty. So it's not attached to a particular beneficiary. The escrow contract might specify certain conditions of who can fulfill this service request and who can be the deliverer, but it's not necessarily the case. It can be just the first person who satisfies this. And also there's another type of conditional bond which is called a commitment. A commitment is itself like is kind of related to swear. So it's when a service provider actually swears on each promises to comply with the rules of a game, with the particular service contract. For example, in the case of like a flight aggregation case, you have an indexing service. The promise of this indexing service is the following: I observe your primary data source and data stream, and I'm going to include, like after you update your primary data source, say in the Ethereum name system, 10 blocks after that, the index that I publish is going to contain all the items that you include in the primary source. If I make an omission, or if I attribute a spurious entry to you, or if I make a mistake in the representation, then I stand to lose all my deposit. So this is how this kind of commitment can work. And these are all can be combined from the same type of condition, so from the same kind of notes. The note has particular fields like beneficiary, an amount, a serial number, some validity, dates, and a remark field. So it's actually quite similar to a check or kind of any kind of instrument which has these fields. And most importantly, it has a reference to an escrow address. In the case of conditional notes, this escrow will evaluate whether the promise of a future service, whether in the future that service was actually provided or not. Okay, so far, is it clear so far? So now we turn to the service guarantees, how you give it out. So the first part is that a service provider can issue a commitment. This commitment can be on a case-by-case basis. It's like it can be just issued off-chain and presented to the swear contract, or it can be a long-term promise that, hey, I'm actually an indexer node, and anytime you chug a task at me, I'm going to just index your things, and you can just rely on it because I register this kind of service promise with a valid until date on the swear contract. So you can think of the swear contract as basically a generic registry of these commitments. And you can think of it as also, there's another aspect to think of it as an app store, because a swear contract can actually be a kind of curated list of particular games these games are basically the rule sets of services, and you can issue your own swear contract, which like contains only references to particular games that people checked that they are sensible. So it's kind of a bit of external or enforced quality control possible there. So the swear contract is a mapping from node identities to games contracts. So a game contract is basically a contract that describes all kinds of rules of a game, and the game contract is placed together with the swindle contract. The swindle contract is basically the courtroom, the judge, that knows how to orchestrate a trial, how to organize the stages of a litigation, and how to ask the witnesses based on the resource data that you find in the game contract. So what are we talking about here? In the case of a litigation for, like, if you're a travel agent and you actually find that the flight aggregator indexer left out your offer and that's why you lost a lot of business, you want to sue them, then basically the swindle contract will follow the rules of the game, which will say that, okay, if you litigate for the case of omitting a data entry, then the first stage of litigation you have to present the inclusion proof, like a proof that in your original data source, this actual offer, like offer of a flight from Budapest to London, was actually included. Okay, so you provide that Merkle proof evidence to the witness contract, and when the judge asks the testimony from that witness contract, then the witness contract can simply say, yes, this is a valid proof. Actually, that data source really contained this offer. And the judge simply ticks it and advances the trial to the second stage, which is requiring proof that same offer was not actually in the aggregate index. So it was actually a proper omission. And there's ways to do that as well, how to provide certain inclusion proofs and Merkle proofs to provide evidence that something was omitted from an index. I hope I don't have to go into the details of how to do that. It's easy to do based on the fact that in an index things are ordered if they are correct. So you can just show the two sides and see that there's nothing in the middle, so it was omitted. So and what happens, and if the judge finds that evidence also stands up to scrutiny, so the second stage witness is also saying that evidence against the service provider is valid. Then it advances the trial stage to the verdict and says that, yeah, this guy is actually guilty, and gives back the execution of the guilty verdict back to the swear contract, which actually goes back with an authorization note, goes back to the swap contract, which holds the deposit. So the swap contract holds the deposit that you put up as a service provider against your promise for compliance. And if the swear contract is valid, executing the trusted verdict of the judge, then basically it acts as an executor and confiscates your deposit from the swap. Or actually the swap kind of gives it to you. And here actually you can see this generalization. So a commitment, as I said, the commitment was just another promissory note. A commitment is actually nothing else but a type of conditional bond. So it's a service request. How can that be interpreted in real life? Well, it's basically a service request because you request the jurisdiction, or like you request the legal system to provide evidence that you didn't comply to your own rules, and if they provide that service that they actually prove that, then you give them the bounty of your deposit. So you can interpret a commitment and a litigation and the verdict against you as a service request. So it makes a lot of sense. So you see that, like, from very, very, very simple little ingredients like these promissory notes and a very generic judge contract and a very generic execution contract, you can put together a very complex service economy where you can have like millions of nodes communicating each other in a peer-to-peer way, and completely, in a scalable fashion. Like they all provide all kinds of services to each other, like indexing, like storing files, and I mean, I deliberately mention examples which are kind of closed system examples, but you can even imagine like real life services to be part of this. In those cases, the escrow witness will be I don't know, the Amazon readers review, review score or whatever, something that goes out in the real world, or maybe even a jury that actually votes using Fabian's identity thing. They can be put together like as a kind of voting body. So what you see here, it looks like a bit of a decoration. This is actually just supposed to show you that the swindle contract, if you follow this idea of escrow witnesses and stages of litigation, then basically the jury process, the trial process, can be represented as a finite state automaton, where the states of the automaton are basically the stages of litigation, and the transition labels are based on the outcomes of the testimonies of the actual witnesses. And so as the swindle contract, or the judge sitting in the swindle contract, the imaginary judge, as it goes through the testifying witnesses and asks for their opinion about certain evidences, it basically advances the trial in certain stages. The starting stage of the trial is the accusation, like choosing what kind of aspect of the rule set was not complied with, and the end state of the finite state automaton is a guilty or non-guilty verdict. I depicted the non-guilty verdict with green and the guilty verdict with red. So this is basically and the beauty of this is that this is composed of like very abstract and very simple and well understood schemes. So you can think of this whole framework as like building up like complex things from little Lego pieces, the reasoning about which are relatively easier and therefore hopefully provide less error-prone implementations. So next I'm going to talk about the most important thing, the extension of these services to proper networks. So what are we talking about here? So far we talked about peer-to-peer interaction and the possibility to use the blockchain for service guarantees, but the interaction itself was like peer-to-peer. However, as in you might have heard with advanced payment channel implementations like Raiden, or even if you take the Bitcoin's Lightning Network, that the interesting bit starts when you can actually compose payment channels into a network. What's the benefit of doing that? Well, in Swarm, the Swarm network, the peer-to-peer interaction happens with a limited peer set, because it's based on a semi-permanent constant connections with your peers. So I typically interact with, let's say, a small number of peers like Fabian and Julian. These are my peers, and the whole idea so the reason why these payment instruments like the checkbook and the payment channel works is based on the fact that we have repeated dealings with each other. We have a constant traffic because we constantly deal with, do business with each other, and therefore, because they are recurring, I can accumulate checks and cash them in bulk. However, this is very limited because typically what I want to do is I go to a sandwich shop in Southampton and I want to interact and do business with that person probably only once in my whole life, and this person is not my peer, first of all, and I certainly not expecting to do repeated dealings with him. So when you compose payment channels into a network, this is exactly this problem that it solves. It extends the capabilities of the system from repeated dealings with a small number of peers to ad hoc one-off interactions with any two nodes, between any two nodes. So this is actually what the network does. So what we're talking about here is that you see on this diagram ABCD, which are, each of them are like, connected with just, so A connected to B connected to C connected to D, in this sense of having a payment channel or having a swap channel between them, which is about repeated dealings and a stable connection. But in this case, A want to interact with D, for example, they want to send a payment, simply want to send a payment because they walked into the Southampton sandwich shop and I want to buy a sandwich, and that's what they want to do. And in this case, what happens is simply this sequence diagram. So basically, A will issue a conditional bond. Yeah, I pay you if you give me that sandwich, or maybe this is not the best example, but like, just imagine like you have a conditional bond that A issues to B. B can take it over because they have, you have guarantees that if the service is not provided, then of course you don't have to pay for it. So they can just, you can just have like a sequence of local peer-to-peer interactions and like compose them into a indirect transaction between A and B. And if the service is such that you need some sort of receipt beforehand, before the actual delivery happens, then that can be done as well. So it's basically similar to there's a post analogy to this, is like certified delivery. So you basically get notification back to A that yes, your offer was accepted or something like this. So basically, once again, like if you compose these payment channel and checkbook like swap channel solutions to a network, then you get an extension in terms of frequency and reach. So you have like a very, very robust off-chain scalable solution. The only assumption that you need to make here is that the network of nodes has certain graph properties. Basically, you have to make sure that from any node to any node, you're guaranteed to have a route. So you're guaranteed to, in the graph, that any node is connected in a healthy fashion. So there's always a way that I can reach the Southampton sandwich shop through starting from my known peers and connections, and in a small constant number of steps, I can do that. Now, I don't want to go into too much technical detail here, but there's an interesting problem here, which relates to the fact that it's not only necessarily just the route that's needed, like a guaranteed route, but actually, just imagine if I want to buy a sandwich that's like 5 Ether, but the link between B and C doesn't allow them to allocate 5 Ether to actually buy that condition bond from me. Is this kind of clear? So there's a kind of a throughput restriction on these channels. So the guy simply doesn't have a deposit like a collateral in the channel that allows them to kind of in advance take that conditional bond and basically sell it to C. And the one interesting solution to this problem is like to have a way to allocate certain deposits to various channels, so between peers, without actually touching the blockchain. So we mentioned that like per user guarantees can be done with setting a hard channel deposit. So basically, it's in like a payment channel. You put a deposit up on the blockchain, which gives you some leeway. So your counterparty knows that you have 1,000 Ether locked up there, and that collateralizes, for example, these conditional bonds that you take over from a peer. But what happens if suddenly the opportunity presents itself that like, hey, this guy wants to actually send like $100,000 or what, I don't know, that's just a silly example, like, or wants to do some like really good business, and I have the opportunity to take quite a nice transaction fee for it, but actually I don't have the money in the payment channel, so the next relaying node like C won't actually take that node from me because I can't promise them that I'll be solvent when they give me back the So they actually take care of the delivery of the service request, but actually I will not be able to pay because I go insolvent by then. So what's the solution for this? And there's an interesting construct which is called soft channel deposit, which allows you to kind of dynamically reallocate resources between various peers in your checkbook contract without actually touching the blockchain. How this works is a bit beyond the scope of this talk, but just one hint that it's based on the idea that basically you have to do an agreement with all the peers in the checkbook, and kind of, so if I promise to Fabian that, hey, I allocate actually, so please Fabian take my conditional node, but because I promised to you that I allocate $200 to our channel, then Fabian only believes me if he actually gets a note from Julian saying that, okay, Julian doesn't want that 200 pounds, that 200 ether that's in the checkbook, and he kind of countersigns, so they kind of agree how we're going to allocate these resources. And the interesting problem is that this kind of consensus only works really if you can make sure that the allocation table, so the allocation table that I issue, in this case is unique. So the problem can be reduced to prove the uniqueness of the resource allocation table. And then the peers can countersign it, and then they can be happy that they can be absolutely 100% be certain that I'll be solvent by the time the conditional note, the conditional bond matures and the delivery takes place. Was this a little bit more cryptic than before, right? I think it's a bit more difficult, but so the idea is that there's a construction by which you can more flexibly reallocate resources from channel to channel without touching the blockchain, and the effect of that is that you can mitigate the throughput restriction problems in swap channel networks. So if there's suddenly like more resources needed between two peers because they are on a route for a lucrative transaction, then they basically can quickly reallocate resources from other peers that are not using those resources at the moment. So this kind of hopefully solves problems or make them a little bit better. So once you have these swap channel networks, you can define interesting other constructs from them. For example, you can have like you can chain together certain conditional bonds, which correspond to like a task which is a complex task, like a pipeline. That like I add certain things to the service and send the resulting product to someone who had some other value-added service. So you can basically chain the conditional bonds together in a protocol which defines a supply chain of some complex product. Or you can define the famous atomic swap, which atomic swap basically means that for example you want to do an exchange of like $300 for an ether, and you put up a bounty that like, hey, here's $300. Please give me the best deal that you can, and if I accept that deal, then the whole transaction goes through. But the whole point is that my $300, I only want the $300 to be actually transferred if I accepted the offer and I can be 100% sure that I get that 1 ether back. So it's like, that's why it's called atomic swap, because it's in one atomic move, the whole transaction either happens in its entirety or doesn't happen in its entirety. Like it's that construct. And interestingly, with the escrow conditions, atomic swap can be defined as a kind of as a kind of logical end operator, basically, over the escrow conditions. So when I send the conditional bond for my $300, basically the condition will be that you send me back another conditional bond, another offer, and plus it has to be true that both has to happen in order for the final transfer to be released, or like the final transfer to happen. And so examples of these kind of complex constructions can be like, for example, the crash proof of custody for storage insurance that we use to incentivize preservation of files in Swarm. So this is basically the storage insurance I was talking about. This is going to use a kind of proof of custody construct. So what is proof of custody? Proof of custody is a cryptographic construct that somehow makes sure that you have, it's somehow a proof that you have a piece of data at a particular time. In a way, you prove that in a way which doesn't require you actually retrieving a whole file. So it's somehow you put up a challenge that proves in a compact way that you store a piece of data without you having to retrieve it. And the crash proof of custody is an interesting. It's like a structure that optimizes to put together a proof of custody, like a proof, for example, an entire website like Wikipedia. So it defines a protocol that comes up with an initial input, and the output is just a single hash, and that single hash proves that the Swarm, the whole network of Swarm as such, actually does contain and preserved the entirety of Wikipedia with every page and every chunk of every page. And that's a kind of cool construct because it can be shown that it's really optimal in terms of network traffic or like bandwidth consumption. And that can be implemented as basically a competitive bounty over like this combined conditional bounties. I hope that it's kind of more or less clear. And other examples are kind of database insertions where you can outsource the insertion into a database, so you don't have to calculate the new index, for example, when you insert an item, but you just throw the new item at the storer node that holds the root key, the root hash of the old index, and they somehow take care of recursively organizing how the nodes are added to the database that's stored in a distributed way in Swarm. And other examples are like mailbox or chat history or like persistent Facebook comments or something like this. And these services can also be implemented with this idea. It's a little bit hand-wavy, admittedly, so obviously without me providing you the formal code or working code, this is a little bit hand-wavy, and I admit that, so this is at this stage, this kind of research. So that's about it. I mean, we can go into details if you want to ask questions, then with pointing you to ways to interact with us. We have just started a collaboration with various external entities and the foundation members as well on 5 sub-projects. We have 5 working groups. One of them works on the Swapster and Swindle framework, so we already started implementing the smart contracts for this and also the off-chain interactions. And you can visit the GitHub channel for Swarm. You can look at our homepage for the orange papers and the research papers that we wrote, and you can follow us on Twitter. Thank you very much, and let's go for questions.
Okay, I have a question, Viktor. So basically, are you working together with Raiden? Because this is very similar, right?
It's very similar.
The basics implementation is very similar.
Yeah, it's
the same research topic.
Yeah, it is.
So are they in the research channels?
Yeah, it's very similar. I always invite them. They haven't showed up yet. But yeah, it's very similar. So basically, what I talked about this. When you have the payment channel implementation with these checkbook contracts, and if you put them in a network setting, that's basically you get Lightning network. I mean that's or Lightning or that, it's basically the same thing. The only difference, which is like I have to admit that these advanced payment channel networks, they actually include implementations of the atomic swap. So without actually implementing the atomic swap in the escrow condition, I can't really say that they have the same level of functionality. So only together with the atomic swap implemented escrow conditions can I say that they are on the par with the Raiden network, yeah, or Lightning, yeah.
Another question here. Can you just shout it out?
Yeah. It sounds like the accounting protocol goes way beyond just supporting file storage, which is still what I thought Swarm was all about. Do you envisage that whole network of promissory notes being required to run the file storage network, or do you think it actually in practice the initial file storage network will only require a subset of those?
Yeah, I think a subset would be enough just for the storage. Just for the storage node would be enough, the subset. But these different instruments are actually super easy to implement. So these are really just a few lines of additions. I mean, maybe it's a bit exaggerated, but like really not a big deal to implement. I mean, the real promise of this whole thing is that the same generic network of like this swap network can run all kinds of services at the same time, and that has a lot of advantages because you can pool your deposit resources, for example, over all kinds of tasks, like not only the sandwich shop purchase, which was kind of a joke, but also like let's assume that you pay your Spotify, your decentralized Spotify listens, or like when you visit the Wall Street Journal and read and have a paywall, then you pay from there, or you pay for storage, or you pay for all the database indexing that you do from all the same networks. So it's kind of that's where the real gain happens when this, if it ever happens that it's kind of mass adopted to these services, then you have the benefit of amortization over these various services. So just imagine that you ultimately keep at each time at each point in time, you basically keep 20-30 maximum 20-30 active peers, and you deal with them, and you take care of all your payments that you ever needed, and hopefully scaling to like Visa-sized transaction volumes, hopefully.
One more. Just shout it out.
Okay. So with your litigation system, does it allow for off-chain litigation? So rather than a smart contract deciding on a situation, a traditional court, for example, and if so, how will it pass the verdict back into the chain and treat it as a trusted resolution?
I mean, practically, like, so the thing with these litigations is that most of the time, unless it's like this, it's the jury or voting body case, actually, most of the time, the participants know the outcome of the thing. So you actually know whether you're guilty or not. So most of the time, you'll be better off just giving it up and say that, okay, I was guilty. Let's not burden me with even paying the extra transaction cost for submitting the evidence that I already know the outcome of. So these judges will actually be quite idle, and most of the time don't do anything because everybody will know the outcome of the result. So basically, the answer to your question is that there's not much to do on-chain anyway, because off-chain people can already check with the smart contracts whether certain evidence is check out or not. Maybe you can give examples when it's not the case, because there might be some time lag with the result in advance, but
I mean, the specific example I was thinking of was the Ethereum name service and
Yeah.
the deeds that are there. There is no way, if there is a dispute about the deeds, to carry that out on chain. There's no way at all to actually transfer a deed to, if we decided that someone is a new legitimate owner, to transfer it to them. So that would require something, for example, where you would need, I don't know if we build it as a commitment, so it holds the deed and will release it to whoever.
I haven't really thought about it, but I would really appreciate if you walked me through the example in detail sometime, because then you might contribute some interesting ideas how to do it that even more scalable. But in general, the the litigation itself would not have too much volume. So I mean, here usually, because of the deterministic nature of these things, the normal operation would be compliance. I mean, that's the hope, obviously. Because if there's too much non-compliance, no one will use the system anyway, so it's kind of a little bit pointless. So so what I'm saying is that there's no real scalability issues related to the swindle or the litigation. Yeah.
One last question, I guess.
Not really
Or
a
just a
question, but like an
comment, yeah.
addition here. Basically, if you have a way to like run through kind of the smart contracts and it will come out with a certain outcome, there's no incentive anymore to even like make the problem in the first place, because you know it will be like ruling against you, right?
Sometimes if you're indexed a node, like maybe your hardware equipment just, you know, again, it can fail, or maybe your hard disk fails and you just lose that chunk, even though you knew that if you lose it, you will be punished. But of course, in Swarm, there's a lot of redundancy, so that's probably not going to be a real danger to people, that the hardware failure immediately leads to them being punished with losing all their stake. But this is kind of just a side issue. Yeah, but your point is correct.
Cool. One last question. Anybody? Okay, I guess that's it. Thank you.
Thank you very much, guys.